On to the next slide. So before we start this week's material, I want to super quickly review what we learned last week to make sure it's fresh in everybody's heads, because we're going to build off of that. Next. So yeah, two of the biggest things we learned last week were the number of factors of something and the sum of all the factors of something. And to find the number of factors, we find their prime factorization, we take the exponents, add one to each, and then find the product of all of these. And this works because the problem we're trying to solve here is basically like find the number of paths through these factors, right? If they are tiles and we're trying to like jump from tile to tile, we have 4 possibilities for 2 to the third, 2 possibilities for the 5, and 2 possibilities for 17. Because we can choose one from each that's like up to the exponent and also including 0, because we can always pick 0, like yeah, just to have a factor of 1. So this is why we have the formula for the number of factors. Next slide. And for the sum of the factors, we're also doing this kind of like path selection. You can think of it that way. Except now we want, for every single possible path, it represents like 1 factor, and we want to add up all of those paths. So the formula is for each prime factor, we take the sum of all of its powers starting from 0 up to the exponent. We sum through all the prime factors, and then we take the product of all of those sums. Next slide. And that works because it's kind of like the distributive property, like the extended distributive property, where you you have every possible combination of some selection from each prime factor. And if you expand it all out, that gives you the sum of every single factor in that number. Do you guys remember this part?
Thumbs up, thumbs down.
If you guys have any questions, just direct message it or message it in the everyone's chat, and we can go over it. Cool. Next slide. Yeah, so this week let's change it up a little. So let's say we have a question that's like find the number of even factors for 40,500. This is number I picked because it has a really pretty prime factorization. It's 2 squared, or 2 to the 2, 3 to the 4th, and 5 to the 3rd. Right, so next slide. Yeah, we know how to find the number of factors because we learned that last week. But this time we don't want odd factors. We only want the even factors. So how can, the idea here, which is we're going to do it throughout today's lesson, is like, how can we modify this formula just a bit and filter for just the even factors? Yeah, so Alrisha has her hand raised. Do you want to say something?
I think you have to like, for like, you know how we have to like list out like 2 to the power of 0 to the power of 1 to the power of 2 to find out the number of factors. I think you have to like doing the even exponents. I don't know, something like that.
That's a good idea. So it has something to do with the exponents. And you're trying to enforce evenness, right? So let's reveal the answer for this first one for even numbers. If you think about what makes a number even, it means it's divisible by 2, right? That's what an even number is. You can divide it by 2, and it goes in evenly. So a number is even if and only if it has at least 2 to the power of 1 inside of it, meaning like that prime factorization includes 2 to the 1. This could also be 2 squared or 2 cubed, right? Because those are all divisible by 2 to the 1. So 2 to the 0, if a number only has 2 to the 0, or like, you know, it just doesn't have 2 at all, that means it's not even. What this boils down to is we can exclude 2 to the 0 from consideration during our strategy and just continue as before. Next slide. So yeah, here's this in action, right? So if you have 2 to the 2nd, 3 to the 4th, 5 to the 3rd, The number of factors, if we don't filter for just the even ones, we have 2 plus 1 times 4 plus 1 times 3 plus 1, because there's 2 plus 1 options, right? For the first prime factor 2, there's 4 plus 1 options, 4 tiles for the prime factor 3, and then 3 plus 1 options for the prime factor 5. This is kind of like we're counting how many different paths exist. But this time, as we count paths, we want to remove the tile that is 2 to the power of 0, because that one is anything that has that tile in its path is not going to be an even factor. So we can remove 2 to the 0, which in this case, it means we don't do the plus 1. We don't do that, add that last one tile. So we can just do 2 times 4 plus 1 times 3 plus 1. And this gives us 40 factors. And yeah, next slide. So if we were to find the sum of even factors for this number, it's the same idea. We don't want to consider 2 to the 0. So whereas like usually we would add the sum of all the powers, right? 2, 3, and 5. You can see in the expression there. We just don't include 2 to the 0 because that represents the option for the pathway where the factor is not going to be even. So you can compute this out again, where it's 2 to the 1 plus 2 to the second, and then the same for all the 3s and all the 5s. And it gives you the answer of like 113,000 something. And that is the sum of all the even factors for our number. I went over that kind of quickly, but is it clear why we remove 2 to the 0 from all these like processes?
Thumbs up, thumbs down, sideways,
Could be sideways. Sideways.
45 degrees.
Okay, kinda. Some up, some kind of wiggly. Yeah, we'll have some visualizations later that'll make this clearer. Let's go to next slide. Actually, let's go back. So somebody sent me a question. They asked like, why isn't 3 to the power of 0 and 5 to the power of 0 still in? Or like, why is it still in? Yeah, this is a good question. Let's think about it, right? So we want an even number. And the way to make sure a number is even is if it still has 2 somewhere inside it, right? Like if this factor possesses a 2 somewhere inside of it, then it is even. So we can keep 3 to the 0 and 5 to the 0 because those things don't change anything about a number that make it even or not. So for example, one of the factors that's come out of this like huge distribution, right? If you multiply it out and get a ton of like little numbers to sum up, we get like 2 squared, right? 2 to the second power times 3 to the 0 times 5 to the 1. And that gets us 20. It gets us 4 times 1 times 5, that's 20. That's still an even number. Having 3 to 0 didn't change anything. So if there's 3, 5, 7, or other prime factors, those we can just proceed as normal. Yeah. The only special one is 2 because 2 indicates, the presence of 2 indicates whether or not it's even or odd. Okay, next slide. Okay, so this time I want you guys to try it for odd. So I just changed it up a little bit. So this time we're finding the number of odd factors for 40,500. How are we gonna handle just the odd numbers? Does anybody have ideas? You can message in the chat for everyone. And Coach Roma, can you monitor the chat?
Yeah.
Private or to everyone?
Sorry, what did you say, Isabel?
Private or to everyone? Do we send it in private chat or to everyone?
Coach Owen, should they send to private message you or send to everyone?
Private message. Or is there an option to message me and Coach Roma?
It's okay. Just send it to Coach Owen. So yeah, remember the question is asking how many odd factors are there in 40,500? One factor would be 1. 1 times 40,500 is 40,500. So the question is, how can we find the number of odd factors? And we might want to think about how we found even factors.
Okay, so right, a factor is odd if it's not divisible. So I got some answers from you guys. They're really good. So some of them say, yeah, so a number is odd if it's not divisible by 2, right? So we want to make sure, kind of the same way last time, we made sure we have at least 2 to the 1 inside, or like more than 2 to the 1, right? Like 2 to the 2, 3, 4, 2 to the 10, whatever. This time for odd numbers, want to make sure it's the exact opposite. It doesn't have any powers of 2 inside. And if a number doesn't have any powers of 2 inside, here's a trick. You can always give it 2 to the 0, right? Like for any number, when we say 40,500 is 2 to the 2, 3 to the 4, 5 to the 3, we're also implying after that 5, there's 7 to the 0, 11 to the 0, and you can go to infinity, right? Like all the other primes in the entire universe are to the 0 for this number. So if there's no 2 in a number, you can just pretend there's an invisible 2 to the 0, because 2 to the 0 is 1. Yeah, and proceed like that. So you can do this by, yeah, so this time, as we find the number of odd factors for this number, we kind of do the same number of factors like path counting with the round tiles. But this time we're removing what is 2 to the 1 and 2 to the 2. So if there is any prime factor of 2 in this number, we just set it equal to 1. And then for anything else like 3 and 5, we proceed as usual. There's 4 plus 1 and 3 plus 1. And it's times just the 1. That 1 represents 2 to the 0. So no factors of 2. And this will give you the number of factors that are odd. Someone else also had a really good idea. So if you can also, because a number is either odd or even. So if you find the number of even factors, you can just find the number of total factors and subtract out the even ones. And that gets you the remaining odd factors, which is exactly what is happening here. Because if you were to take the expression, we can do this at the end, but if you take the expression for the even number of factors and subtract it from the expression for the odd number of factors, that gets you exactly what you see here, because it takes out the 2. The 2 is what we kept last time for even. And the 1 is what we're keeping this time for odd, where Coach Woma is waving his mouse. So they're like, if you combine both of them, the even and the odd factors, you get the total number of factors. Yeah. This is a little harder of a, I think it's a little harder of a topic this week. So we'll try to take it slow. We'll have some visualizations in the next couple slides. And I will answer all of you guys' question afterwards. So if we want to so on this slide, so if we want to find the sum of the odd factors, same thing. We do the sum of factors, right? The same formula we learned last week. And this time we remove 2 to the 1 and 2 to the 2. We take those out. We only consider 2 to the 0 and do the sum of the product of all the sums. And that gets you this new sum that's 18,000 something, which is the sum of all the odd factors. Yeah, and somebody asked, could you go back to the last slide? somebody asked here, like, shouldn't we multiply rather than add? Well, we're adding, so remember each block of parentheses is the number of round tiles in that like visualization that Coach Woma had last week. So that's why we're adding inside the parentheses. We're counting the total number of tiles, vertical tiles right under that prime factor. That's why we're doing 2 plus 1, 4 plus 1, 3 plus 1. Because there's like 2 to the 1, 2 to the 2, plus 1 to the 0. And there's 3 to the 1, 3 to the 2, to the 3, to the 4, plus 1, there's 3 to the 0. That's why we're adding. And we're multiplying because we want all the possibilities for like each tile as we jump from tile to tile, counting the number of factors. It's a little complicated. Yeah, let's move on. We're going to have some visualizations in the last section. Next. Okay. This is something that some of you might already know, but it's worth talking about because we're going to talk about squares and cubes. So a perfect square is a number that is, it can be represented as another number times itself. Like a square, right? Like when you find the area of a square, it's like side length times another side length. So these numbers like 4, 9, 16, and 25, these are perfect squares. Is this part clear to everyone? Slash, have you guys heard of these before? Thumbs up and down. Okay. And similarly, we have, yeah, so a square is a number times itself. Another thing to notice, and this is important, is if you take the prime factorization of any square and you look at the exponents, all of the exponents are going to be multiples of 2. And this is because if you think about it, a number, when you have a number and then you multiply it by itself, all the exponents are added to itself. So all the exponents double. Next slide. You get 2 copies of everything in the prime factorization. And that means all of your exponents are going to be even because you just took that same number and you multiply by itself and all of its exponents double. So yeah, for example, if you look at, let's look at the second example, right? 60 times 60. What's the prime factorization of 60? It's 2 to the 2, 3 to the 1, 5 to the 1, right? It's 2 times 2 times 3 times 5. If I get 3600, which is a square, because I multiply by itself, all the exponents double. It's 2 to the 4th, 3 to the 2, 5 to the 1. Because it's like that big multiplication just like got multiplied by itself. And you have like twice as many of each factor. Yeah, so this is a good way to, if you ever don't know if a number is square and it's like more like 784 and you don't know off the top of your head it's 28 times 28, you can look at its prime factorization. Everything is even, it has to be a square. Next slide. Yeah, and something useful is like for the smaller numbers, like I would say like for all the squares under 1,000, it may be useful to memorize these. So you have them off the top of your head. It's not that memorizing is more important than understanding, but just for speed, because oftentimes you're not going to have forever on like contests and stuff. It's useful to see something like 256 and just know, oh, I've seen that before. That's like the square of 16. So this is something useful, I think I would recommend. Next. Okay, similarly, a perfect cube, it's a number times itself 3 times like cubes because you have like height, width, and length, right, in a cube. So mathematicians call these perfect cubes because they can be represented as some number multiplied by itself 3 times. Yeah, and the exponents are going to always be multiples of 3 for the same reason that squares have exponents that are multiples of 2. Next slide. So yeah, for example, 6 times 6 times 6 is 216. That's a cube. And the prime factorization of 6 is just 2 times 3, like 2 to the 1 times 3 to the 1. And if you repeat it 3 times, you can check this for yourself too. The prime factorization of 216 is 2 to the 3rd, 3 to the 3rd. Yeah, And for 8,000, it's the same. It's 2 squared times 5, that's 20. And then when you cube it, all the exponents triple. Next slide. Yeah, and similarly, I think it's useful to like know off the top of your head some like easy cubes. So all the cubes under 1,000, some of which are squares, you should also see. Those are, yeah, those are, I think, useful to memorize. And some of the bigger ones, maybe not as much, but yeah, at least those few. Also, a question for you guys. So what's a number that is both a square and a cube that you guys see?
64.
Yeah, 64 is a square. It's 8 times 8, and it's a cube because it's 4 times 4 times 4. I think there is one more.
125.
125 is not a square. You guys can just shout it out if you find it. I'll wait like a couple seconds.
Is it 1,000?
1,000 is not a square. It's not a square. The square is 729.
729?
One of you guys might have had it, but yeah, the square is 729 because that's 81 times 81. And
it kind of looks like a square.
Yeah. Well, the challenge problem for this week will be like, what makes something a square and a cube? What's the pattern? Because you can tell from the prime factorization as well. Next slide.
I found another square and cube.
Oh, there's another one?
One.
Oh, one. Okay.
Okay.
Forgot
Just
about the
wanted to
easiest one.
shout out there.
Okay, so yeah, so let's next slide. Why are squares and cubes useful? Sometimes they come up as conditions that you guys need to find factors. So here's an example. So for 144, maybe they won't ask for even or odd. So this question says, find the number of factors of 144 that are perfect squares. So how can we do this question? And
I see Kaden has a question.
Kaden has his hand raised.
It was a comment for the last slide. I found another one. It's 15,625. That's 125 squared.
Yep. Good job. Yeah, that's also a square. And yeah. Cool. So for this one, if we want to find the factors that are just squares, how can we filter those out?
Risha also has a question.
Can you go back to the last slide?
Oh, we have so many squares and cubes. I see.
I noticed that the 4, 9, and 25 are all perfect squares.
Interesting.
Yeah. So if the base number of that, like the base of that exponent is a square, makes the whole thing a square once you cube it. I will give you guys the answer actually, because I think this is super cool. So the reason, so if you have a square, remember the exponent's a multiple of what? Hold up fingers. 2. Right? And if it's a cube, the exponent is a multiple of what? 3. If you raise a square to the power, if you cube a square, it's 2 times 3 in the exponent. So I don't know if that's something you guys have covered, right? But it will be 6. 2 times 3 is 6. So the exponent is always a multiple of 6. And it doesn't matter if you square a cube or if you cube a square, because it's 2 times 3 or 3 times 3 either way. So if you look at the numbers that are both squares and cubes, their exponents in their prime factorization is always a multiple of 6. So yeah, so like 16 would work too. 16 is like 16 cubed is like 2 to the 12, I believe. And 12 is multiple of 6. So yeah, prime factorizations are cool. You can do a lot with it.
Cool.
Okay, let's go back to this part. I'm going to go over this a little quicker and leave some time to do a review and for you to try it out yourselves. So next slide. Okay, here's the visualization. So when we find the number of factors of something, we're trying to count the paths, remember? And a common theme throughout today is like, depending on whether it's even or odd or perfect squares or like, I don't know, whatever condition you can think of, right? Like we're crossing out some of those tiles because those tiles would violate like the rule. So if it's even, for example, we were crossing out 2 to the 0 because that would make something not even, and we're keeping the rest. If it's odd, we're crossing out everything that's below 2 to the 1, like 2 to the 1, 2 to the 2, because those would make it even. And in this case, when we're trying to find factors that are only perfect squares, we want to keep the tiles, these steps that have exponents that are a multiple of 2, because when I complete the path, right, if I pick anything from the 2 column, like 2 squared, and I pick anything from the 3 column, like 3 to the 0 or 3 to the 1, and I multiply it, right, to get my final factor, you'll notice the exponents of that are all multiples of 2 because all of my selections were multiples of 2. So for perfect squares, this is what we do. We only keep the powers of each prime that are also perfect squares, aka their exponent is multiples of 2. So 2 to the 1 we cross out, 2 to the 3 we cross out. If we had 2 to the 5, 7, 9, we would cross those out. And then using the remaining tiles you have left, you can do the same process. And in this case here, for 144, the process is we do three tiles, 3 choices from the 2 column and 2 choices from the 3 column, which gives us 6 factors that are perfect squares. And you can check this for yourself. The 6 factors are 1, 4, 9, 16, 36, and 144. Yeah. So 4, for example, is like 2 squared times 3, 0. 36 would be 36. 36 is 2 squared times 3 squared. And 144 is 2/4 times 3 squared. So every path that we counted is a perfect square. How do you guys feel about this so far? Up, down, middle. Okay. Some up, some middle. Okay, nice. Next one. Okay, this one we can try by ourselves. Or sorry, we'll work through this together. This is going to be our review round because it's a lot of exercises. So this time I'm changing up the constraint again. So I'd like us to find the sum of all factors for 9,000 that are divisible by 15. And to speed this up a bit, next slide. We'll start with the prime factorization because I'm confident you guys all know how to do that part. 9,000 is 2 to the 3rd, 3 to the 2nd, 5 to the 3rd. Next slide, next step. So from there, we also know the sum of factors. We'll also do this part, right? So for sum of factors, remember we add the entire tower. We add all of the tiles. So 2, 0, 2, 1, 2, 2, 2, 3. We add all of the 3s. We add all of the 5s. And then we would multiply those 3 sums. That's the regular sum of factors. Next step. This time,
yeah.
What's up?
Oh, I was wondering if anyone knows what we would do
Yeah.
to make sure that all the factors we're summing are divisible by 15.
So some of them are going to be divisible by 15 and some of them aren't. And we want to modify this so that we don't include the ones that are not divisible by 15.
I think I know.
Let's give it, if you think you know, please message me privately. Okay, I'll give it another half minute, and then we'll talk about the answer together. Okay. Let's talk about the answer. So I think somebody said they have an idea.
I think Caden.
Yeah. So you have to find the normal sum of the factors, but since it's divisible by 15, it has to be like 15 or 30 or like that. So if you have 3 to the 0 and 5 to the 0, then that would not multiply out to a multiple of 15. But if you take like 3 to the any power times 5 to the any power, there's gonna be like 15. And then if you multiply that by like 2 to the any power, that will still be a multiple of 15. So basically you find the sum, but then you subtract the 3 to the 0 and the 5 to the 0 from the parentheses.
Okay, so if I heard you correctly, what you're saying is we do sum of factors, but this time we remove 3 to the 0 and 5 to the 0. Because in the 3s and the 5s column, if we ever pick 3 to the 0, that means we don't have enough like 3 ingredients to like make a 15, right? And we don't have enough, if we pick 5 to the 0, we don't have enough 5s inside to make the 15. If we pick anything that's higher than 3 to the 1 or higher than 5 to the 1, we have enough factors in there to make it divisible by 15. Yeah, that's right. So except, yeah, we have to have at least 3 to the 1, 5 to the 1 inside each factor, which means as we do sum of factors, we need to make sure those are selected. And that's the answer. So if we can do the rest of the sum of factors the way we usually do, and you can do this on pen and paper or in a calculator, and you'll find that the sum of factors is 27,900. Yeah, so a common theme with closing statement here. So a common theme with prime factorizations, you'll realize is like, there's this interesting relationship between multiplication and addition, division and subtraction, and exponents. Exponents are kind of like the next level above multiplication and division. So you notice you do like a lot of addition and subtraction with the exponents that feels similar to if we say like something is divisible by 15, we subtract like 3 to the 1 and 5 to the 1 here. So yeah, as you do more of these problems, you'll like notice these patterns too. If that was confusing, ignore what I said and you will be fine.